Hello, Organic Chemistry. Here is my first poster for Chapter 10 on alkynes. I read the first 3 sections, and here's my thinking on the first 3 sections. So, just a definition to start off. Alkynes are compounds that contain a triple bond between carbons. So, at some point in the molecule, we have 2 carbons that have a sigma bond overlap and 2 pi bond overlappings. And they're sp hybridized carbons. So next section I read, it was about the nomenclature of alkynes, so IUPAC naming, and the rules look pretty similar to what we're used to. Again, number 1, identify the parent, identify substituents, number the parent chain. The parent chain does have to include the pi bond, or the 2 pi bonds, or the triple bond, and then assemble substituents alphabetically. Not a whole lot different than what we're used to. So I included an example here. So my parent chain would start here at the top carbon and work its way, having the most carbons possible with the triple bond being part of that parent, and the triple bond has to have the lower locant number. So I numbered 1 through 7 going this way, which gives me substituents at 3. I got a propyl at 3. I've got an ethyl at 4 and a methyl at 5. So putting that all together alphabetically, the ethyl would come first. So I got 4 ethyl, 5 methyl, 3 propyl, and then the 1 identifies where the triple bond is. It's on carbon 1. And then since the parent has 7 carbons, it's hept, and then ine would identify the alkyne. Another possible way of naming this would be to pretty much the same at the beginning, 4 ethyl, 5 methyl, 3. But here, instead of calling it propyl 1-heptine, we would call it 3-propyl hept 1-ine. So just kind of rearranging the 1 with the hept. So either method is fine. Continuing on, that was IUPAC naming. There's common names for alkynes, all based on the simplest alkyne that can occur, which is ethine, and that's given the common name acetylene. So acetylene and ethine are the same structure. So a common name, we would use acetylene as the base name, and we would just name the substituents that attach themselves to the carbons in acetylene. So the IUPAC name for this structure would be propyne, or the common name would be methyl, since we have a methyl attached to the acetylene, so methylacetylene. And this would be called a terminal alkyne because we have a hydrogen attached at the end. So the triple bond is on a terminal carbon. Another example of common naming would be, here we have 2-butene. We have 1, 2, 3, 4 carbons, so it's butene, and the triple bond is at carbon 2. So 2-butene would be the IUPAC name, but the common name, so we have acetylene here, and we have a methyl group on each end, so we would call it dimethylacetylene. And this would be considered an internal alkyne because the triple bond is not on the end carbon. So a couple of examples of different types of common names. And then the last section that I read was about acidity of terminal alkynes. So comparing what we have here is just an alkane, an alkene, and now an alkyne. And if we were to look at the pKa values for each of these, we would see that the acidity increases as we go from an alkane to an alkene to an alkyne. So basically that proton right there on ethine is easier to deprotonate than that proton on ethene, which is easier to deprotonate than the ethane. And the logic behind this, it's all based on the stability of the conjugate base. So if we were to remove that proton, we would get an sp3 hybridized orbital with an extra electron, causing a negative formal charge. And since this area of electron density it's pretty far removed on average from this nucleus of this carbon, that it's not as stabilized. So this is a less stable conjugate base. So as you can see, as we go from sp3 to sp2 to sp, this should be sp hybridized, these areas of electron density, they become more condensed, therefore they get closer to the nucleus of the carbon, and that stabilizes that negative charge. So we have a stability of the conjugate base happening as we go from sp3 to sp2 to sp. So terminal alkynes are, in terms of a base, they're not as strong as an alkene or an alkane. Okay, so lastly, I wrote what bases could deprotonate an alkyne. So if I wanted to deprotonate that hydrogen right there, what base could do it? And it would have to be a very strong base. And amides and hydrides are common strong bases. So an example of what that would look like, let's say we use hydride, it would come and deprotonate the hydrogen, electron pair would dump onto the carbon, so that would give us an acetylide ion and hydrogen gas. So that would be the mechanism for the deprotonation of acetylene with hydride. Okay, and that's what I took from the first 3 sections. That's my poster, and I'm going to use that to try to answer some questions from the review guide, and I'll have that on Thursday for you. Have a good one.